Good evening, class. We are looking at chapter 2, limits and derivatives, section 2.1, the tangent and velocity problem. Okay. Again, you may use your initials because we are recording in case you have any issue with recordings and privacy. In this chapter, we will cover aside from this section, the limit of a function, calculating limits using the limit laws, the precise definition of a limit, continuity, limit at infinity, derivatives and rates of change, the derivatives as a function. Previous sections that have been covered in chapter 1, for example, 1.4 was important, exponential functions and their properties. Logarithmic functions and their properties, and the relationship between the two is that the two functions are inverse of each other. That's extremely important, okay? And so, with that being the case, let's move on. All right. All right, class. So we are looking at the tangent and velocity problem. And basically, the tangent has a specific definition that you can see here, and it means just touching the curve. So according to Euclid, a tangent is a line that intersects a circle at only one spot, and that's fine. Okay. However, let's see what happens as we move on. Okay. So what does it mean? The line intersects C only once, but it certainly does not look like what we think of it as a tangent line. On the other hand, the line T is a tangent line, although it crosses the function more than once. Meaning what? Meaning the Euclidean definition doesn't work here, everybody. Okay. All right, so what is the idea behind the limit? Okay, finding an equation of a tangent line to the parabola y equals x squared at a given point, the pair is 1, 1. So let's see the concept. Everybody knows how to find an equation of a line. We need two things. We need a pair and we need the slope. Now, if the slope is given, so be it. If the slope is not given, you need 2 points to find the slope, okay? So what happens here, we only have 1 point. And so one way to do that, we can approximate it by finding, slope of lines nearby, by picking up a point nearby, okay? Now, when we connect that, the line that we are coming up with, it's called a secant line. It is called a secant line. And so we can find the equation for the slope. If you recall, it's rise over run, the average rate of change of y with respect to x. Y sub 2 minus y sub 1 over x sub 2 minus x sub 1. So with that being the case, we are using, class, we are using the definition of a slope. Okay. So this is the definition of a slope. Okay. Rise over run. Okay. And if you pick a point in general has coordinates x comma x squared, okay, this is what you get. Now let's go and pick up some point nearby, such as x being 1.5. So if x is 1.5, remember what this is. This is x. This is y, or x squared, okay? That's 1.5 squared is 2.25. You calculate the slope. Again, you pick the number, a point close by. Now take a look at this table, okay? This is very simple, but it is tedious. It takes a little bit of a time to generate that. So you pick up a few points nearby, you do the calculation, and you come up with the slope of a secant line. As you can see on the left column X, okay, we start from somewhere, like number 2, and we get close to 1. Notice even 1.001 is not close enough. I want you to see that. This is coming from one side of X equals 1. Specifically, we are coming from, okay, let me just show you. This is X equals 1. We are approaching it from the right, and now we are approaching it from the left. Okay, so I hope you see what happens. We are approaching it from different angles, okay, from the right, from the left. So when we look at the right side, and if we look at this column, everybody, the last number we see 2.001. And if we look at this column, the last one, okay, is 1.999. Why am I using the last one? Take a look at this is the closest number to 1. And over here, this is the closest number to 1. So I hope you realize we can guesstimate the limit to be somewhere between the two. If you have any doubts, you can go with 1 point more 0, 0, 0, 0, 0, 0, 1, and then 0 point more 9s, 9 and a bunch more. And I hope you realize the limit seems to be equal to 2. Okay. Now, this limit, okay, when we take the limit of the slope of a secant line as q approaches p, that's how this is read. The limit of a slope of pq as q approaches p. That seems to be 2. We have a pair, we have the slope, we are basically done. The rest is easy. We can come up with the equation of a line. Remember the point slope, y minus y1 equals m times x minus x of 1. And so basically, as q approaches p along the parabola, the corresponding secant lines rotate about P and approach the tangent line. So take a look, okay, from the right, from the left. That's how we arrive at them. And that's the idea behind finding the concept known as a tangent line. The next problem is a velocity problem. Here's an example. A ball is dropped from an observation deck 450 meters above the ground. We want to find the velocity at a specific point, or in this case, 5 seconds. We are following the free fall objects, Galileo's law. S of t is 4.9 t squared. It's really half of gt squared. I hope you remember the basics from physics. And so what's happening, and we'll discuss that further later on, okay? So we want to find the speed. If you recall, the average speed is the total amount of distance over the total amount of time. Okay, it's very simple. If I cover 100 miles over the course of 2 hours, I'm doing 50 miles per hour, but that is on the average. Now, instantaneous velocity is at a specific point, in this case at t equals 5. So I don't know how to calculate that yet because I need 2 points. So again, we are going to do the same thing. Number is 5. We are going to pick up numbers nearby and do the math. Okay, so let's do that. As an example, if we pick 5.1, which is fairly close, then we can plug it into S, or the position or the distance function. Okay, 5.1 as well as 5. The difference is the total distance covered. And the time is 5.1 minus 5. And therefore, we can calculate the average speed, okay, in that time interval of 5 to 5.1 to be 49.49. And the units are meters per second. Now, let's actually look at a table. This is, again, tedious. It takes a little bit of a time, but it's very straightforward. We calculate this, and we have the following numbers. I hope you see that what's going on here, okay? As we go this way, okay, we are getting closer and closer to number 5 here. Take a look. This is the closest one. So if this is not good enough to give you the answer, you can do more by going with 5 less than or equal to t less than or equal to 5 point and add more zeros, 5.0000001, if you will. I hope you see that the answer, therefore, it must be 49 meters per square second. So as you can see, the instantaneous velocity can be easily found from the table as 49 meters per square second.